Magnetic force on a moving electric charge. A proton, here's its charge, here's its mass, traveling horizontally at a constant speed of 5.40 times 10 to the 6 meters per second, enters a uniform 0.750 Tesla magnetic field. On the diagram, show the direction of the magnetic force on the proton as it enters the magnetic field. Then, B, show an approximate path of the proton. C, calculate the magnitude of the magnetic force on the proton. D, calculate the acceleration of the proton. And finally, calculate the radius of the proton's path in the magnetic field. So the first part, find the direction of the magnetic force. So we use the right-hand rule, point the four fingers of your right hand in the direction of the charge's velocity, which is to the right. Then curl your fingers perpendicular to your palm and point them in the direction of the magnetic field, which is out of the page. Finally, extend your thumb perpendicular to your fingers. Should be there already, frankly. It is pointing in the direction of the magnetic force on a moving positive charge, which is what we have, and that is down. Since the magnetic force is at a 90-degree angle with the velocity, the proton will describe a circle, like the moon orbiting the Earth, because you have a constant force that is always perpendicular to your motion. So that'll be like this. Okay, you've got a semicircle there. Next, oh, by the way, how did we find that out? Well, we knew the force was down. We found that from part A, so that just starts changing the velocity like this, making it move in a circular motion. Now here's the trick. Once it leaves the magnetic field, there is no longer any force on it. So at this point here, you take a tangent to the semicircle and you find it going in this direction. So once it leaves that magnetic field, it will go straight down. So it's a combination of two motions here. Let me just erase that so you can see it more clearly. When it's inside the field, it describes a semicircle. The moment it leaves, it moves off tangent to that circle and goes in a straight line. Part C, find the magnetic force, the magnitude of it, and we use our QVB, where B has to be perpendicular to the velocity, and it is, right? The velocity is coming this way, and the magnetic field is out of the page. So we just substitute in our givens. There's Q, there's the velocity, there's the magnetic field, and we get a force of 6.48 times 10 to the minus 13 newtons. Now calculate the acceleration of the proton. Well, we start with Newton's second law, and since we want the acceleration, we divide both sides by m, so we now have it in terms of the magnetic force and the mass. Well, we have the force. We came up with that on the previous slide. We were given the mass. You divide through, and you have an acceleration of 3.86 times 10 to the 14th meters per second squared. And finally, calculate the radius of the proton's path in the magnetic field. We have our centripetal acceleration formula because we're in uniform circular motion here, and we solve that for r. So basically we just crisscross, multiply both sides by r, divide both sides by acceleration, and we get this. Now we have our given velocity, which does not change. The magnetic field will not change the velocity of that object, the proton, and we calculated the centripetal acceleration on a previous slide. So can you see how these different steps build on each other? Now, let's say you got this wrong and you had an exam and you got the acceleration calculated wrong on a previous page. If you did all this work, the teacher should give you a correct for data, and even though your radius is wrong, should mark this question correct because you did everything right. You just had the wrong given from the previous slide. So you put those numbers in and you get 0.076 meters or 7.6 centimeters.